Okay. So yeah, I change a little bit the title of my talk. I mean, just to give something a little bit more exciting than E plus E minus collider. And so what we will be focusing on for the program of the 4 lectures will be to reach the rare B decays and talk about, beyond the standard model effect and what we expect to discover with more statistics. So I will focus mostly on E plus E minus, but I don't hesitate to refer to some LHCb measurement. And so if I summarize a bit the lectures, not necessarily in the order of the 4 lectures, but just on the content, the idea will be to give a flavor of how to study elementary particles, and especially how to put the different elements we need for an experiment on B physics. Of course, I will make some reference to indirect searches, and I will do some analogy, of classic, or let's say standard, information we have in particle physics from the past, and how you can make an analogy of what we are doing today in our quest of new physics. I saw many of your lectures focus also on the why we are looking for those new physics, and I will more focus on how we are looking, how we will do that, or how we are doing that. And so that's why I make some link, maybe sometime a bit naive link with the older experiment, or what I remember of it, and how I can make this parallel to the Belle and Belle II experiment. So now we have 2 generations. Belle is the past, but the foundation of our experiment of Belle II today, which just started to take data a couple of years ago. And so, as I said, I will mostly focus on rare BDKs. And according how it goes for the first few lectures, I might add a little bit of outlook for the first lecture on CP violation, which I think is also interesting. But in 4 hours we cannot treat everything. So I think rare BDKs is a hot topic these days, and I will explain why. So for me, LHCb and Belle II are just 2 approach of the same quest. Like there is many of those kind of case along the history of particle physics, and this is very good sign. I mean, in the sense of you bring different systematic, you be different strains together, and I think the combination of both is enrich, in fact, the field, and push people well beyond what they usually would have down if they were more isolated. So I think it's all about it in this kind of workshop to see that. And of course, as I said, hot topic, because we are talking about, depending the person you are talking with, hint or anomalies or sign of new physics, and some, for some more ambitious people, even some first sign of new physics. So just a couple of words on my background. As I said, I mean, I spent quite a, but this is a case of actually most of the colleagues lecturing during this lecture are also the organizer, like Jim, spending back and forth according their opportunities or their interest between E plus E minus at different energy, or a PP bar or PP, for example. PP bar, I will talk a bit about Fermilab, and PP, of course, for LHC. I put LHCb in my case where I had these opportunities, but also B physics in LHC means CMS, like you will have a seminar later next week. Okay, and that's finally allow you also on the way to travel back and forth in the different continents of our world. So so most of my let's say time on flavor physics was spent actually around the experiment at KK. So maybe, I mean, you're a bit less familiar with KK than CERN. So just I put a couple of slides to put things in geography, the location. So KK in Japanese means in fact a high energy accelerator center, and it's located in Tsukuba in Japan. And well, I think I put first largest accelerator facility in Japan, certainly, but it may be also in Asia, in fact. And also because of the diversity, we are focused on B physics, but here I show the map of Japan, Tokyo here. I don't know if you can see my cursor. I hope so. So Tokyo here and a little bit more in the north. KK, in fact, there is two centers, one which is called J Park, more on the smaller experiment and fixed target, and KK, which is a location where the B factories, so where are located Belle and Belle II. Okay, so there is a nice view from above of the KK campus, and you know, from this view you can already see the ring, and just to give you the scale, the ring has a much smaller circumference than LHC, and so something like 3 kilometers. So you see, this is a whole campus of KK, and you know the ring barely fit. And as you can see also in the lower part, in the lower left part, you can see the LINAC where you're gonna prepare the two beam electrons and positrons at different energy and accelerate until you inject them to the storage ring, the two storage ring, okay, respectively for E plus, E minus. So you actually have a very nice overview, and you see how it's, you know, it's really a pocket experiment, especially in compared to the size of CERN, which extend well beyond the CERN campus. So here you have everything within a very nice opportunity to, and the photon factory I will not talk about. But so Belle was the experiment. Belle and Babar were the B factories. So after the Clairaut generation, introducing in fact asymmetric collider in the B physics world. And as I said, we will talk about why asymmetry of beam energy later. But for now, let's say that mostly a successor, if you want, of the Argus and Cleo experiments in a very similar condition, which for Belle and Babar, basically taking data during about 10 years. This is a typical case of those experiment. And starting around end of mid 99, so 10 years, and for Belle until 2008. Okay, and as I was saying, Belle II is a successor of Belle, and you know, it took almost 10 years, so it takes as much time to build or design, and build actually more to design, but to build an experiment, basically to replace the following experiment is take about the same time as the data taking amount of time. And Belle II looks very much like Belle, I mean, especially from outside, or where a lot of components were reused. And I mean, location exactly the same, but with I mean, very significant upgrade in the inner part of the detector. And the main goal of Belle II is to collect 2 orders of magnitude more data. So everything that Belle was doing quite well with the statistics of 1 inverse attobar in integrated luminosity, Belle II is proposing to collect 50 inverse atomar, so 50 times more statistics with at least the same quality and performance of the detector. So I will not go very much through the standard model. You got several lectures. So we will be focusing very much on the third generation because basically what I was talking about, the interesting hint, seems to be in fact showing differences between the first generation behavior, let's say, which seems more standard model-like, whereas some effect seems to be visible in second and third generation. And as we are mostly focusing on B physics, I mean, third generation concerned here, we will, we will have something to say, and I will discuss about it. Of course, here as a very generic introduction, the impact of flavor physics, only just by considering the three parameters of the standard model and the one you have to measure precisely and to see if those are consistent, I mean, are showing a very, a flavor impact. And also one slide I show here, which is in fact a poster of an earlier school a few years back. And you see, I like the, accumulation. You can play the game to try to recognize the different, discovery, which pave or a field of particle physics, especially in, here, especially in the experimental side. And you see many of those plots actually that I will show along the lecture. And so showing again that the flavor is very active. And as we will discuss a bit later, that indirect search, not only complete the direct search, but in some cases, while expecting that coupling to new physics are high enough, then increase or reach a possible reach in terms of energy, in some sense, indirectly. So here in this slide, I just show a classic, and this will be a bit the analogy I will be doing for this classic experiment of Rutherford. And the parallel we are doing between the experiment and the interpretation and the validation, or at least the search of new physics. In this well-known experiment, probing for the atom itself. And for me, in the interpretation, the standard model is a bit the pre-experiment of Rutherford standard model. This Thomson model versus the new physics, which is on the right part, the Rutherford model, which in fact is more consistent with the experiment itself. So seeing the detectors a bit as OIs, and the setting, the observation made allow you to, let's favor one version of the theory versus, or one model, theoretical model versus the other one. Here, and this will be the point of the lectures, the following lectures. The first is that it's a very good example of indirect search first. And the second part is that, the importance of controlling the experimental setting is actually what is the most important, because, here in this case, you need a good control of the beam, and we will discuss a little bit about the accelerator, a good shielding, or a good, shielding by shielding from the outside background. And in the case of Belle, Belle II, this will be a good shielding from the beam background, from the particle from the beam, which will in fact invade your physics events and might lower the performance or the quality or the efficiency of your analysis. and also a good coverage of the detector. So in my naive analogy here, as you can, I mean, very well known, if part of the coverage was not available, then you might not even have observed the effect, which allow you to make this distinction between these two theoretical models. Okay, so now let's talk about modern particle physics experiment. So, I mean, here I start very basic information. So let's say the effect of particle over the different detector, and so explaining the design, the standard design. That's why most of the detectors E plus minus will look very similar. Here, what I put on the left side as a different particle. One thing you have to know already is that B physics actually will have a large range of final state particles, and you want to cover most of them, if not all of them, which will allow to reconstruct what you can reconstruct. And at the same time, as we will see in the third lectures, which will allow you to constrain the part like the neutrino that you cannot detect. So this is, let's say, the requirement at the beginning of your design. So now the layering, I mean, the way you order the detector will be decided by the way the particle interact with those detectors. So very quickly, going through this list from photons to neutrons, we are mostly interested actually for the four first one. So the photons will not be sensitive to this magnetic field, of course, and then will interact mostly in the electromagnetic calorimeter. The electron will be similar in their effect on their interaction with the electromagnetic calorimeter, whereas will be seen by the tracking chamber. So already here, it forces, in fact, the ordering of tracking chamber inside the detector and outside the calorimeter. You can imagine if you put electromagnetic calorimeter first, then you will not be able to measure the momentum of the electrons. The muons here also are barely stopped if by the muon chamber. So the only fact that you have heat of a track in the muon chamber, and which is usually very outside, because I mean, all the other particle will be stopped, so you better put it as far as possible. So we'll decide about the location of the muon chamber. And other particles, charged particle, have, let's say, some reaction a bit between what I mentioned for the electrons and the muons, and so we'll decide some location of hadron collimator when you have one. Okay, this is what happened. So now you have the layout from innermost to outer, and this would correspond to a perfect detector if you have like a fixed target experiment. So if you have a beam going through and you want to detect the content of the beam itself. If you have collision now, especially collision going in 3 dimension in all direction for typically, asymmetric, slightly asymmetric or symmetric collision. And then you will want something covering as much, the good coverage I was talking about. And also, you need a magnetic field map. So your tracking detectors need to be inside this magnetic field. And so the location of a magnetic pole should be placed, beyond the tracking detector. So you end up, with this detector cross section, and you can, put all this information we described earlier and see already a typical event display. And this time with just for the purpose of the exercise, but very soon we will we will see a real even display of the experiment. So just to give you general information from the present, from the past, and and the ongoing experiment. So I was talking in red about Belle and LHC B, and so at completely different energy, and I will come back to this, and E plus E minus versus PP collision. Again, concerning this E plus E minus collision, we have a long history and a lot of important information from competitive experiment from Belle, which is called BABA, which was located at SLAC, and the older experiment, more symmetric experiment in energy, Argus and Cleo. So I put that. For LHCb, so I would say that, I mean, definitely an amazing success of studying B physics in PP collision, so a very harsh, very difficult environment with, let's say, a particularity or in a very important improvement on particle identification. So this is, for example, compared to an earlier experiment, CDF and D0 at Fermilab, this time on PP bar collision at lower energy. Pave the way of B physics actually in those kind of environment, but with some weakness of concerning the particle identification, especially the separation as we will see between kaon and pion. And whereas LHCb has basically, if not as good, even better than a B factory separation between kaon and pion. And again, everything in a quite difficult environment, which get even more difficult with high luminosity. So I put here CMS again, I don't know, and Atlas, I should have put Atlas also, I mean, experiments which have interesting things to say in B physics. And Guy Wilkinson will cover in later lectures about the LHCb. I will say, as I said, few words when introducing some of the interesting hint of new physics. Okay, just a small 1 minute break on something interesting, the logo of the experiment. So the name and logo of the experiment are not always, let's say, help you to remember what it is about. In the case of Belle, I wanted to help you a bit to memorize or to remember. So Belle in French means beautiful, which is, well, I mean, very clear that the purpose is, I mean, one of the main purpose, not the only one, we will see that later, is to study B physics. And you can see clearly the B here as a logo. But, smart undergraduate students propose this very fun logo, where in fact, if you rotate the logo itself, you start to see also E versus E at a bigger font for the second E. So let's say electron at higher energies and the positron in the back. And you start to see the collider itself, the asymmetric E plus E minus collider, producing those B's that you see in the left. So now you will forever remember what Belle is about. Now the question you might have is why, I mean, which energy and why is this energy? So I mentioned already earlier about 10 GeV, 10.6 GeV. So let's see why we are running at this energy. So that's why we call it actually intensity frontier, instead of energy frontier for the LHC experiment. So LHC experiment, I mean, increase, especially when you saw compared to CDF D0, drastically the energy, whereas compared to Belle II stay at the same energy, but increase, as we will see, the luminosity, increase the density of the beam to increase the luminosity and consequently the statistics. So why at 10.6? I mean, you know already. So here I just summarize epsilon meson discovery and the B quark discovery. So actually showing the proposal of that time to run, to have sufficient statistics. So here you see that at that time, it's quite ironic in some sense that epsilon, production was the rare decay of that time. So you needed 100 billion protons striking the target to obtain only one epsilon. Whereas now we are basically an epsilon super factory, where actually a billion of epsilon are produced, daily. So here, in this case, you have enough energy to produce and to observe dimuon resonances. And when you do the invariant mass of these dimuons, these opposite charge muons, then you find with, already fixed target with 400 GeV proton beam, you see a resonance around 4.5 GeV. And just to take some, distance, and when I was talking about, first hint and anomalies, I found this also, I don't know if it's true, but the oops, Leon, I mean, an earlier observation, quote unquote, of the epsilon at 6 GeV, and which turned out with more statistics to actually not be an epsilon, but just a fluctuation. So this things, you might be close to a real observation, and that's what observed at 9.5 GeV. But before concluding too fast, you have to have enough statistics, and this is an excellent illustration of it. Okay, so epsilon 4s, because as you have noticed, I'm talking about 9.5 to observe the first epsilon 1s, and so the presence of BB bar. But actually, you are running at 10.6 GeV. So why 10.6 and not 9.5? So 9.5 here, I show you, in fact, the different epsilon. So you see here the invariant mass in function of invariant mass. We were here to discover the B quark. And now we are running at 10.6 GeV in center of mass. So what happens is production here, I list here of the epsilon. So for 1s, 2s, and 3s, actually you are under the threshold. So typically 5.27 GeV for the mass of a B. So below that, in fact, what the decay you are producing, which a large cross section, actually much larger than epsilon 4s, are mostly through this bottomonium decays, and which are mostly what I described here in terms of gluon, gamma gluon, gluon, and hadronic modes. And whereas to produce real B, so to become a B factories, you need to be above this threshold, and so at the epsilon 4s. And actually, I mean, again, what you see is the cross section at 4s is smaller, but that's the price to pay, let's say, to get B mesons. So do you produce only a B mesons? So actually epsilon events are mostly BB bar events, so B plus, B minus, or B0, B0 bar, and nothing else. So this is why often people, and you will see in the event displays, talk about clean physics. The environment is 2B and nothing else. And this will have two important impacts. One, for the rare BDK search. It means when I was talking about neutrino missing energy, is that what you, let's say in general, don't detect are possible candidate for neutrinos. So this will be a very important property that we will discuss later. For the CP violation, what another important part is that actually that the two B mesons are created in a coherent state. So you have B bar always until one of it decays, and the other B can change a flavor B0 to B0 bar. So this will be also one very important ingredient. So even if, as we will see later, the cross-section are not as high as what we will get at PP, for example, in the production of B mesons, this is, those events are clean, and the efficiency of tagging them for the flavor or for the B content is extremely high compared to those experiments. Here, I just mentioned that unfortunately, we don't produce at epsilon 4s energy, we produce epsilon 4s, but also this higher cross-section actually from what we call continuum. So I go very quickly, so I put a little bit more information, but for the interest of time, I will just summarize here the cross-section and for the different lighter quark. And those will form, in fact, the background, what you mostly have to distinguish or to disentangle from the B physics you are looking for. So this will have a huge impact that the efficiency, you have to fight against those events. So use some of your efficiency to detect with a high purity BB bar events. And for that, you use some information on the shape of the events. When you have BB bar events, it's more spherical because the B are almost at rest or a very, very small boost compared to the two jet of QQ bar, which are more along, let's say, an axis as it's illustrated in these figures. So you have high cross-section and comparatively to the BB bar. So typically 1 nanobar, and I will explain a bit more. So here a few slides on accelerator quickly. So what you want to say, is what we want to remember is what we will do is rare decays. So basically B decays at the order of 10 minus 5, minus 6, or much lower. So you need a large quantity of collision. We talked about the cross section here earlier. So I just put some information everybody know, but just to remember of the cross-section unit. But cross-section at a given energy are fixed and known as described earlier. So what you will have to do to improve the number of collision is to improve the luminosity. So in summary, with a cross-section of 1 nanobar, with 1 inverse femtobarn, typically you have 1 million of BB bar pairs. Also, this is the luminosity you accumulate, for example, for these 2B factories over a decade. And when you are down, it means when your funding agency think you are not anymore in the race, or yet you have done enough, or you cannot do much more, then the experiment stop. And and then that's so. I said 2008 for Babar and 2010 for Belle, and that's time to go to the next experiment. Very quickly, I'll try to show now, illustrate the point I did about the particle detection applied to the Belle experiment in a nutshell. And so here for you, maybe still illustrated by this slide, this figure in Japanese. Maybe it's not yet completely clear where to put the detector. And so let me just summarize. So this is the translation of the previous slide. And you can distinguish now in 2 parts. So let's focus quickly on the tracking device. So the tracking device, I repeat, will be in the inner part of the detector, and will be made of a drift chamber. I will show some pictures just in the next slide. What is important is the drift chamber will give you all the information on the momentum. of the particle and the charge of the particle. And the silicon vertex detector are, the detector you have at the center, few layers of very precise heats, which allow you, in fact, to reconstruct vertex, so the decay point of the B decay, with a resolution of typically less than 100 microns. And within, of course, a solenoid. So with a magnetic field of 1.5 Tesla mentioned here. So very quickly, yeah, this is how you will measure the momentum, and you can do extremely easily this exercise of relating the momentum here to the magnetic field of 1.5 Tesla, and the radius you will be measuring in your detector in this large drift chamber of typically a radius of few meters. Okay, so yeah, here for purpose of illustration, I'm showing the central drift chamber, which was built for here for Belle, but similarly for Belle II with smaller cells, which allow for a better resolution. So that, let's say, the upgrade. But the principle is the same of those drift chambers, and in fact provide for each tracks. Typically, you see you have about 52 layers of those sense wires, and typically provide 50 heats. And those heats have in R5 a typical resolution that I put here of 130 microns. And so these are the components to measure the momentum and to know the charge of your particle. And again, for this complete inner part detector, part of the tracking, this time the resolution is much better. However, the price to pay is you have much more material, as you can imagine. So this gas chamber has very low material budget. So this is why you can do a huge volume of this detector. If you had to replace it a bit like CMS detector by only silicon layers, then you will have to have much larger momentum. As you can imagine, as we are working from B meson almost at rest at 5 GeV or so, then the typical momentum particle range is from, let's say, 200 MeV to 2 GeV or so. So you have to be very careful about the material budget. However, you need this resolution, a very precise last hits close to the IP, close to the collision point, to measure as precisely the B vertex of, as I was saying, something like less than 100 micron. This is your, let's say, your requirement when you design the detector. Then, of course, the resolution of those hits, especially in Z information, because in central drift chamber, I was talking about mostly the R5 information. You have an information of Z because actually you have a slanted angle of some of these wires, but the resolution in the central drift chamber is only of order of few millimeters, 4 or 5 millimeters. And this is much too bad resolution compared to the vertex determination of 100 microns. So you need this silicon vertex detector, which are typically 3-4 layers, where the resolution, heat resolution is typically 30 microns. So here I'm getting a bit, missing some time, so I will not go very much in the PID part, but basically here also the idea is to combine the detector and ordering them by their material budget. So keeping the one which are the most costful in terms of losing particles outside, and those performance I'm showing for particle ID allow you to distinguish what I was saying, typically to select with an efficiency of 90% and a very small fake rate, so contamination from pion of 10%. So typically, those performance allow you to distinguish between kaon and pion, and that's what I put for the previous few slides. For neutral detector, very quickly, so we talk about gammas and of course K short. So for gammas, for pi 0, for example, decay into gamma. So those two gamma I was talking, those two photons, then you collected their energy in the electromagnetic calorimeter will be combined to form the pi 0 and the candidate and see the invariant mass and select them. Whereas the K short, also a neutral particle, will be identified here because of longer lifetime. So with a displaced vertex, so here this time in order of centimeters, so even outside very often your silicon vertex detector traveling quite far and being a displaced vertex from the IP to pion that you form the invariant mass. I put some illustration here of event display. So to justify what this is real data, and this is very early Belle experiment. And you can now really apply the very simple recipes that I showed earlier to understand the event you are seeing, actually, event by event. So here, typically, you can see, the behavior of electrons, the clear tracks, and the deposit in the electromagnetic calorimeter. Whereas here, an event here of heavier leptons, the tau, where you see typically a tau decaying with an electron, so leptonic decay of one of the tau, and the other side, most probably a 3 pions new decay, so the hadronic decay of the tau with a high branching ratio. So this is what you would see. And an event here which looks with more tracks, which looks more and more like a B physics tracks, and a fully reconstructed events here where you distinguish muons from other particles, and with their invariant mass see a JEPSI that you can combine with kaon and pion to do these JEPSI K-star events in one side, and the other side, which is also fully reconstructed. Okay, and by building the vertex for each of them, what I was promising in terms of resolution, then you can apply it on real data, and you see typically the separation of the two vertexes. With an asymmetric collider, the 2B are boosted forward, and you see away from the IP a clear separation from two vertex on the Z direction. So now I will take 5 minutes to talk about now from Belle to Belle II. So as I said, I had more slide on Belle in terms of explaining the detector, illustrating the detector. Here I want to do it to Belle II and to show, in fact, the improvement in terms of the detector. A lot of the outer detector remains the same because the performance are good enough, and because of the price of the detector, we cannot always afford to upgrade, or at least with no reason. One thing which has changed a lot or upgraded a lot is, in fact, the speed of the electronics, to just oversimplify, which allow you to have much faster data taking. So the window, the event window, if you want, where you collect the physics event information is much smaller, allowing you, in fact, of shielding yourself from the background. You remember when I was talking about good coverage, good shielding. So typically, the fact that you can take those events much faster, and so a narrower window of in your data taking allow you to be less sensitive, if you want, to the beam background for the same luminosity. And as the luminosity should increase very quickly, then the background also increase. So you need to prepare for it. And other efforts were made, in fact, to minimize the material. I show, about a combination of particle identification detector for Belle. Here, in the case of Belle II, is try to be as less material as possible in front of the electromagnetic calorimeter. So it has two effects. One of them is you have more room for the drift chamber, so you have a better resolution of your momentum. And the other is you have a better efficiency for your calorimeter, a better resolution, because you don't have, or you have less material in front of it. So this would be, let's say, the ingredients of an improved detector over what we get in the first generation. For the innermost detector, the stress is also of improving the resolution, and you introduce, instead of this silicon strip detector, on top of it, or let's say inside of it, some pixel layers, so much better resolution detector, as close as possible from the IP. With a smaller beam pipe, you get closer. Now we are just beyond 1 centimeter compared to 2 or 1.5 in the case of Belle. So the importance of the collider, this is let's say, in terms of detectors, as we have seen, there is a challenge. Of course, there is this improve electronics. You implement this faster DAQ for the data taking to sustain this amount of data and trigger as fast as possible and as efficiently as possible the events of interest, and not recording a background which will overwhelm your data rate, if you want. But everything is about accelerator, because again the challenge is 2 orders of magnitude in the luminosity. And I have just a few slides to illustrate it. And so here it's a, let's say, naive view of the previous KB. So KB is the name of the accelerator. And so from KB to super KB, the idea is to have a denser beam and as many beam as possible, as many bunch as possible, sorry, in your, so typically the separation of 2 bench is typically of 2 nanoseconds, and having denser beam allow you to have more bunch crossing with a collision. And you see, always on perspective of the previous accelerator, the many accelerator over the last few decades, in function of the luminosity, you see that your jump from KB to super KB in terms of luminosity is highly non-trivial, especially when you compare to the past. You expecting in few years to do as big jump with conditions which become harder and harder to control. So this is what I was talking about when we talk about nano beam. So we squeeze, in fact, and the quadrupole in charge of squeezing those beam become closer to the IP and allow to reach those conditions that I summarize in the next slide are the major ingredient to improve the luminosity. There is two components actually. So the size here, the squeezing of this beam by, let's say, factor 20 are actually the most important ingredients to reach this factor 50. And the increase of the current is another one. So here, this is probably the limitation you will get. You could increase the current more and more, but I mean, actually, this technically not the way to go to reach this luminosity. That's why this part of a nano beam scheme, this squeezing at IP and this all you know, new quadrupole close to the IP are the recipe, if you want, to increase this luminosity. So just to give you a more recent update, so on the Belle II performance, so you had these 10 years to build this improved detector, and this is, you know, déjà vu again, some event display which look very similar to what we had in Belle, and with you know, quality which is quite similar. This is just to when the detector was not completed. So during the commissioning, the first commissioning of phase of the accelerator, what we call phase 2 in our jargon, where you start to see, you know, events which look here more like a BB bar event. So for the few remaining slides, I just want to show you, you know, some of the, I mean, go together to some of the reconstruction and try to reconstruct a B events together. So earlier I explained about photons, I explained about, you know, pi zero, and you can see in real data, we don't talk about inverse femtobarn, we talk about the first few data of the first day of the Belle II experiment. You combine gammas and see clearly a pi zero. So as a you know, experimentalist, you will select all those candidates with invariant mass pi zero inside the, you know, I mean, close to the peak of the known pi zero mass. And similarly, what you're gonna do with electrons is to reconstruct typically JEPSI in their leptonic decays. The famous K-short I was talking about, the neutral particle kaon, which flight a few centimeters, and it flies so away that actually it illustrates well the importance of having a displaced vertex. And I mention it, I insist on it because this will be one of the key for LHC B, that the B are boosted so much that in fact they look a bit like K-short in a B factory environment. So those displaced vertex allow you to distinguish from a background which decay or which come from the primary vertex or the interaction point. So you can see here that not only you have a very nice resolution, but also a very low contamination. Whereas for particles which come more from the IP, like here the phi into kaon, you will see that the combinatorial is much more important because the combinatorial come from this primary vertex. So those are a very nice first data information, very exciting part. And you go one step further and you decide to combine them actually to at this stage to reconstruct charm. I mean, the workshop is supposed to be about charm also. So let's start with charm because we have plenty of them. So with these limited statistics, combining, you know, kaon and pion that you have well separated, you start to do, you know, flavor physics actually. And you see the many decays of a charm, which are illustrated here. And concerning the B, you will look for the most favored decays. We will talk about rare B decays later, but here I want to focus in standard model dominant tree components. So this will be, let's say, for hadronic, B to C UD, so with this diagram, which will give you in one side a D, some of the D you just reconstructed, that you combine typically with one pion or few pions here. I give you something which Saurabh can use a bit as an exercise for the tutorial, is actually, even if they are dominating, you can see this with one inverse femtobarn, you only can reconstruct a 10 of those dominant B. So you have to account for an efficiency of reconstruction and the, the different intermediate state decay, typically charm to kappa in this case, which lower your sensitivity. So this is a way you reconstruct. You have two observables. I showed earlier the invariant mass. For the B itself, we take, well, we reconstruct, if you want, also the mass of the B. So typically, this will be what we call delta E, which is the energy of the B you have reconstructed in the center of mass compared to the energy of the beam in the same center of mass. So they should have the same value. That's why this delta E is typically center in 0. And you will do, you will form another variable we call the beam energy constraint mass, where this time we substitute the energy of the B when you calculate typically the invariant mass of the B by the energy of the beam, which give you, if you want, an independent variable with a very good resolution, and so separation from the background. I just put all the ingredients together, and now with the many possible final state, we start together to reconstruct real Bs. And you see, as I promise, with very limited statistics, you will see forming a peak around the delta E equals 0 and around this MBC around the mass of the B, which proving that you have this time observed Bs through many of its possible dominant decays here. And that will be the end of the first lecture. Can you hear me?
Hi, Karim.
Yes.
Yes.
Okay. You scared me. I thought I was talking 1 hour.
Sorry, I was just admiring these plots, having not seen them for a while.
Yeah, oh, for 2 years, 2 years. It sounds like, yeah, now we don't do that anymore, mode by mode, right? I mean, now we don't look at the event display since ages. But yeah.
Okay. Okay, is there any questions? Seems not at the moment, but if you have any, Karim will be. So someone's asking about the spherical nature of a B event, the origin of that. So Suban.
Yeah, so typically, I mean, in short, those B are, typically those B are almost at rest. And so there is no favored direction. There is no, if you want, the decay at rest. So the decay product go all over the place. Whereas in the case of the QQ bars, they are much lighter quark, and the particle will be just along direction of the back-to-back, if you want, in the center of mass. So you can see clearly the direction of the back-to-back particle, initial particle. By the way, the slides are available to the students, because I mean, I just wanted to make sure.
Yes,
yeah,
yes,
okay.
they are. They put up the first two, not the third one. Yeah.
Okay.
Okay. So Saurabh's going to talk about the topology in the tutorial also.
Yes.
Good. Okay. I think that's all for today.